Hi everyone, let's continue our discussion on energy method. Before we begin, let me give you the review of a previous lecture, was the first lecture on energy method chapter. So let's first start from the first topic that we covered last lecture, which is strain energy and strain energy density for relatively simpler loading. So we considered like a pure axial loading, pure bending, pure torsion, or a little bit complex beam deflection problem, which include both moment M and shear force V. So here we first discussed about the strain energy density or strain energy per unit volume for normal stress and normal shear stress problem. And given this strain energy density, we were able to derive the expression for strain energy of the beam, strain energy of the beam under bending, strain energy of the beam under the torsion, and then we also considered a general beam deflection problem where we have both non-zero V and non-zero M, so that we have two component strain energy from normal stress and strain energy from shear stress component. And we finally for the first time show that strain energy out of the momentum contribution and shear contribution you know can be quantified. And after this quantification, we found that given this condition, like aspect ratio of 10, the contribution from the shear turns out to be less than like 1% of the moment contribution, so that we can use the Euler-Bernoulli beam theory, right? So this is like a new finding that we had in this chapter. After we discussed about this relatively simple loading problem, we considered a strain energy density for general stress state. So as I told you, we have six independent stress component, like 3 normal and 3 shear. And in terms of the multiplication and product of stress and strain, we can write down strain energy density in this way, like total 6 terms. However, if we replace the strain with stress using the Hooke's law, we're gonna have a slightly more complex expression. Still, for any stress state, we are always guaranteed to obtain the principal stress and principal axis. And at principal axis, we can rewrite the strain energy density in this way. Of course, strain energy density should not depend on the coordinate system we choose. This is like a energy, and energy should not depends on the coordinate system we choose. This u and that u must be equal to each other. Okay, so these sigma a, sigma b, sigma c, these principal stress are obtained from the sigma xyz and tau xyz from the previous line. And then after we discussed about this, we also show that strain energy can be decomposed into volume part and deviatory part. The volumetric part is the strain energy that is necessary to cause change in volume change without shape change, and the deviatory term is the strain energy that is necessary to make a shape change without volume change. And we can quantify each of terms in this way, and by using the relationship between shear modulus and Young's modulus and Poisson ratio, we can prove that UV plus UD is equal to UV. We just wrote down in the last page, last line of the previous page. And then as a final topic, we discussed about impact loading. Actually, it does not include any complex or higher level information. We simply use the energy conservation principle. Instead of using F equal ma, and from the acceleration to velocity, from velocity to position, those integrations, if we use the kinetic energy and strain energy conversion without loss principle, then we can find the maximum stress level when the kinetic energy becomes zero, right? So we can by relying on the energy conservation principle we studied back in freshman physics, we can answer several impact loading problem, which necessitate the use of the energy conservation principle. Okay, so these are the content we covered back in last lecture, and let me stop the review at this point.